All right, so now we're going to start talking about this notion of persistent homology. And sort of the underlying issue, if you will, it's like which persistent homology attempts to address has to do with the fact that you're working with real-world data, and real-world data has noise, right? So when you try to extract structure, it's like out of noisy data, there is a question of scale, right? I mean, it's like, so one basically has to distinguish between noise and structure, and that's a subtle issue. Okay, so let me just sort of summarize that real world data is noisy, right? So sort of attempting to extract sort of structure from data requires being able to distinguish between sort of the noise and the data. Between the noise and the signal. Okay. And so this is oftentimes a question of scale, right? I mean, it's like, so one might, for example, assume that something which is small, right, is a noise. It's like in something which is much larger is then a signal, right? So there is an issue of scale. Okay, the idea behind persistent homology, in some sense, is to say that if there is if there's a way, it's like you can introduce scale, it's like into the question of how you extract sort of structure, it's like from your data, then something is more likely to be a signal if it persists over a large range of scales, right? So something is more likely to be sort of a relevant signal right, if it persists over a range of scales. Okay, so we'll see exactly what we mean by this in a little bit as we sort of get into the details. Okay, so one of the issues, if you will, it's like with persistence, okay, or the notion of persistence is that, especially in homology, right? So in homology, if you think of homology naively as, you know, the number of holes of a particular dimension in a space, then what you'll find as as you vary the scale, it's like in the problem, is that holes will get formed and then holes will disappear, maybe because they merge, it's like, or something to the effect. So, so in order to make sense of this idea of persistence, we have to be able to label what happens when holes, say, merge, for example. Okay, and this leads to the idea of the elder rule. Okay. So, so let me try to illustrate this maybe with an example, right? So imagine imagine you're sort of tracking the number of rivers, for example, on a mountain as a function of elevation, right? okay, on the mountain. So of course it's like what happens. It's like is that streams may start forming, streams may merge. It's like and then you want to be able to say it's like which of these streams or rivers it's like is somehow the longest, if you will. Okay. So in particular, what happens is that you have to have a rule. It's like for deciding, how to label. It's like these streams or rivers when they merge. Okay, and this leads to the idea of the elder rule. Okay, so so let's just say that the elevation sort of is increasing in this direction. I mean, which is a little bit counterintuitive, but anyway, so so imagine you have a bunch of tributaries. It's like, and they start forming, and then at some point in time, it's like there's this merger, okay, and then maybe there's another one that starts. It's like, and this merges as well. Okay, so this is just a simple example of three tributaries which eventually merge. It's like to form. It's like one main river. Okay, so and so you can label these things when they first start. Okay. So, so let's just label this 1, this as 2, and this as 3. Okay. All right. So at this point, it's like where it's like sort of stream 1 and stream 2 merge, right? Stream 1 has been around longer, and stream 2 has not been around quite as long. So what we would like to do is we would like to label it's like the thing which is upstream of the merger point by the older or the elder. It's like of the two streams. Which happens to be 1, so we'll say that this segment here is 1, okay, and then the same question it's like arises where it's like when this 1 it's like merges with stream 3, stream 1 again is older than stream 3, so this piece again continues to be labeled stream 1. Okay, so this is what is called the elder rule. Okay, right, that at a juncture right, the two merging paths the older of the two merging paths sort of continues, and the younger one dies, right? Ends. Okay, so so this is just a way to sort of again label it's like these paths. It's like, or as we'll later see, it's like in the context of persistent homology, it's like the homology classes, right? And of course, it's like this makes sense because it's like this gives you the idea that it's like this river 1, it's like it's persistent for a long time, right? So imagine if you now had a fourth river here and doesn't do anything, and second just goes to that point 4, right? So again, we would like to think of this path here as being more persistent than this path here. Okay, all right. So so that's just sort of a basic idea, and then now we want to look at how to do this. It's like for homology, and this leads to the idea of what are called filtrations. Let me just leave the elder rule up here. So okay. Okay. So filtrations. Okay. So we want to formulate this elder rule. Right, for homology groups of all dimensions. Okay, so let's consider a simplicial complex. okay, and a function let's say f from k to the reals, okay, and you want f to be monotonic. And what we mean by that is that it has to be non-decreasing, sort of along sort of increasing chains. Faces. So what I mean by that is that if sigma is a face of tau, what has to happen is that f of sigma is less than equal to f of tau. Okay, so this is what we mean by monotonic. Okay, so what that sort of monotonicity condition implies then is that if you look at the sub-level sets, it's like of this function, all right? So monotonicity implies that the sub-level set let's call that k of a. Okay, so k of a is just f inverse of the half-open interval from minus infinity to a. Okay, so this thing is a subcomplex of k for every a in the reals. Okay, so again, it's like, if you recall, it's like for this to be a subcomplex, what has to be has to happen is that if a simplex is in this it's like a sub-level set, it's like then all the faces have to be in the sub-level set as well, right? So and you see that, right, that if sigma is a face of tau, so if tau is in this set, right, that means f of tau is less than equal to a, right? So let's see now, right? So if tau is in Ka, right, this implies that f of tau is less than equal to a, right? Which means by this that for all sigma which are faces of tau, right, we have that f of sigma is less than equal to f of tau, which is less than equal to a, which implies that sigma is in Ka, right? So that's exactly what you need. It's like for it to be a subcomplex. Okay, and again, it's a consequence of this monotonicity condition. All right. So if you have m is the number of simplices in K, right? If m is the number of simplices in K, right, then you know that if you look at these sub-level sets, right, they're not all going to be distinct for every possible value of the rails, right? The only, I mean, the worst, I mean, the most you can do, if you will, is that at every, it's like, it's like critical value, it's like, it's critical real value, it's where the subcomplex changes, right? In the worst case, you could just add one simplex, right? So, you're only going to get at most, it's like n plus one distinct simplices, distinct complexes, right? Then there are at most sort of n plus 1, which is less than equal to n plus 1 distinct subcomplexes from this sublevel set construction, right? Okay, so you can order them. So you can start the empty set, okay, and that's called at K0, and it's contained in K1 all the way up to Kn, which is the full set, okay. And you can associate, it's like these, it's like K0 to Kn, it's like to the minimum value of A, it's like for which K of A is, it's like one of these things, right? So that's, so if you have Ki, right, you can think of this as K of some AI, right, where AI is the sort of minimum, well, let's just say the infimum, right, actually the minimum value of A such that Ki is equal to Ka, right? Okay, and then so you can think of this as being K minus infinity, for example, right? Which is the empty set, okay, and then this would be Ka1 all the way up to Kan. Okay, and it's sort of easy to convince yourself that these numbers are in increasing order. So A0 is less than equal to A1, An, right? So we call this sequence of complexes the filtration of F. Okay, and it's called filtration because basically what happens is that you have this sort of sequence of nested, it's like complexes, if you will. Okay. And the point, of course, is that we've seen it's like such things before, right? When we talked about things like the, Vitaris-Rips complex or the check complex. So we've seen examples of this before, right? Like the check complex, Vitaris sort of RIPS complex and alpha complex. Okay. We haven't had a chance to talk about Morse functions. It's like, but sort of similar things also show up. It's like when you discuss things like Morse functions. Okay. So in any case, it's like, so there's this nesting. And so the point is that there is a natural inclusion of any complex. It's like, you know, earlier in the sequence into one of the later complexes. Okay. So, so there is an inclusion map let's call that I from let's see, I comma j. So that's a bit of poor notation, right? For ki included into kj, right? And then the point, of course, is that when you have inclusion maps, they induce homomorphisms of the corresponding homology group, right? So this induces sort of homomorphisms of the homology groups. So let's just call that Fp, okay, Ij, and F is because, of course, these filtrations, it's like come from this F function, it's like which we defined on K. All right, this F function which is monotonic. Okay, so this maps, it's like the homology group, it's like on Ki into the homology group, it's like on Kj. So, all right, so in any case, what happens then is that this induces a sequence of homology groups. So let me just leave this stuff up here. So this induces a sequence of homology groups which are connected by homomorphisms, by these sort of induced homomorphisms. Okay, and the basic idea, if you will, is that these homomorphisms allow you to sort of track when some of the homology classes in the previous, it's like homology group persists into the next one, right? So, so imagine if you're going from HPK0 to HPK1, right? Then the image of HPK0, it's like by this sort of induced homomorphism coming from the inclusion, right, tells you which of the generators of the homology persist. It's like in HPK1. And so if you see a generator, it's like which is not part of the image, it's like of this induced homomorphism, then you know that it is a homology class which got created, right, at this point. And then if, of course, this thing gets mapped to 0, then that's a class here which dies or ends. It's like HPK1. Okay, so all right, so let me just sort of state that more clearly. So as we go from sort of ki minus 1 to ki, right, we can gain new homology classes. And we might sort of lose some when they become trivial. Or they merge. Okay, with each other. Okay. All right. So, yeah. So this is what's going to happen, and then we'll talk about this idea of the persistent homology groups. Give you the definition. Right, the PIEF persistent homology groups are the images of the homomorphism sort of induced by the inclusion maps. Right, so let's call that HPIJ, right, as the image under this F map from the ith to jth complex, and which are persistent, and this is for all I and j between, okay, so I has to be less than or equal to j, right, and then the corresponding sort of PIEF persistent Betty number are the ranks of these groups. Okay, and this of course again makes sense, right? So the image, it's like of the homology generators, it's like of a earlier homology, it's like tell you again which of those things are still there. You know, it's like, you know, the ones which started I are still, or not started, but the ones who are present in the ith, it's like complex are still present in the jth complex. Okay, so let's call that beta ijp, right, as the rank of hijp. Okay, and then of course you can also define reduced persistent homology, right, so similarly, right, you can define reduced persistent homology groups and reduced persistent Betty numbers. Okay. All right, so one thing you can observe, of course, is that the inclusion map from I to itself, right, is nothing more than the identity map on Ki in some appropriate sense. So what that means, of course, is that you can get the usual Betti numbers and the usual homology groups from the following, basically from the diagonal, right? So HII persistent is nothing more than the sort of homology group it's like associated with Ki, right? So that's just an observation. And of course, it's like, as we said many times, the persistent sort of homology group really just corresponds to the sort of homological classes, it's like which were present, it's like at the ith complex, which are still present in the jth complex. Okay, so the persistent homology groups sort of consist of the homology classes of Ki, right, that are still alive. At Kj, right, or more formally, what I can do is to say that Hij persistent, right, is you look at the cycles of Ki, right, and you quotient them by the boundaries of Kj, but you have to intersect that with the cycles of Ki, right, in order to make sense of this. Okay, so that's basically what's happening here, and this is true for all p, right? So this is for all p and for all I less than or equal to j. Okay. All right. So let's try to see if we can understand this a little bit more. So let's say we have gamma be an element of HP Ki, right? And we say that gamma is born at Ki, right? If gamma was not an element of HP I minus 1j, sorry, HP I minus 1i. All right, so so we say that gamma is born at Ki if it is not part of the set of homology generators. It's like at the Ki minus 1 complex, it's like which persists into the ith complex, right? So that sort of makes sense, right? It wasn't there before, it didn't come from anything. So if it's there now, it's new, and it was born at Ki. Okay. All right. So furthermore, right, if gamma is born at Ki, then it dies sort of entering Kj, right, if it merges with an older class, as we go from kj minus 1 to kj. Okay, so so this is where it's like we're evoking this elder rule, right? So if one way it's like for you know, it's like homology classes to sort of disappear is if they merge, right? So the basic idea then is that because of the elder rule, it's like we say that gamma sort of ends, if you will, or dies. It's like if it merges with an older class. Okay, so what that means is that so that means is the following. That fi to j minus 1 gamma, right, is not an element of the persistent sort of homology group. It's like from I minus 1 to j minus 1. Okay. But Fij p gamma, right, is an element of h I minus 1 j p. Okay, so let's try to make sense of this. Okay. All right. So this is the generator. It's like which goes from I to j minus 1. So it was born at I, right? So this thing here, right, is all right. So what basically is happening, if you will, is that this statement is more or less saying that there is an older sort of generator. It's like at the I minus 1 stage, which is before it's like gamma, you know, it's like it was born, right? So it can't possibly be the same. Okay. All right. So but if you go from here to here, it's like you'll see that it's it's in that homology group. Okay. So right. So basically, again, it's like what we want to see is that you want to so these two statements together basically tell you that there is another class. It's like which again maps to the same thing. It's like as gamma. It's like, but you know, it's like because of the outer rule, it's like we'll say that the older class persists and not gamma. Okay, so that's why we say that gamma, it's like dies. It's like as this enters kj. It's because this combination of conditions says that A, there's another homology generator which will map to the same thing as gamma does under the inclusion, but that that generator, it's like sort of was there. It's like before gamma was born. Okay, all right. So that is an application of the elder rule. Okay, so this is an application of the elder rule. Okay, then so if now, So now it's like you have some idea of when gamma was born, it's like and when gamma dies. So if gamma was born at ki and dies sort of entering kj, right, then the difference in the function value associated with ki and kj, it's like is the persistence okay. So the persistence of gamma is equal to aj minus ai, right? Where again, if you recall, right, ki is equal to the sublevel set associated with the value ai. And the same thing is true for the j index, right? So sometimes you don't want to work with the function values, you can just work with the indices, right? So there's also the idea of index persistence. Right, which is just is equal to sort of j minus I, right? Okay. So if gamma is born at ki but never dies, right? We say that the persistence then the persistence and index persistence is infinite. Okay. All right. All right. So you can observe that this, notion of births and deaths, it's like doesn't really require that you have actually homology groups, right? This makes sense. It's like for any notion, any sequence of vector spaces, it's like which are connected in some way, shape, or form by homomorphisms, right? Yeah. So, and of course, homomorphisms between vector spaces are just linear maps. Okay. All right. So there's one last thing. It's like which I'll talk about. It's like in the context of persistent homology. It's like before we start talking about how to implement it, which is this idea of persistence diagrams. So we can visualize sort of the collection of persistent Betty numbers. By drawing points in 2 dimensions. So basically, the way to sort of think about this is that for every generator, it's right of a homology class, we have a point. It's like in some 2-dimensional space, whose whose position is determined by sort of the function value. It's like where the homology class was born. It's like, and then the function value where the homology class dies, if you will, right? And of course, it's like to allow for the possibility that it persists indefinitely. We're going to augment the rails. It's like with the plus and minus infinities. Okay. So the point is that so points in 2 dimensions, sort of corresponding to the function values that sort of homology classes sort of were born and died. Okay, so some of these points may have values sort of equal to infinity, and some may be the same. So what I mean by some may be the same is that it could well be that you could have 2 homology classes which were both born and both died at the same time, right? So they're both points on the same diagram, but so in general you have to allow for multiplicity, it's like of those points, okay, in order to really make sense of it. So, right, we have to sort of consider sort of a multiset of points in the extended real plane. Okay, so let's just say r bar squared, right, which is the reals union sort of plus minus infinity squared. Okay. All right. So let's say that we let mu ijp, right, be the number of independent p-dimensional classes. Born at ki, and sort of die sort of entering kj, right? Then you can relate this to the Betti numbers in the following way. Okay, so mu ijp is equal to the Betti number I comma j minus 1 p minus Betti number ijp. Okay. All right, minus the Betti number I minus 1 j minus 1 p minus Betti number I, well, sorry, persistent Betti number, I should say, I minus 1 comma j p. All right, so so you might ask, it's like, what did these do? And if you think about it, it's like it's all about trying to figure out, you know, it's like which things were born, it's like, and which ones died, right, at particular classes. So the first thing in the parentheses, right, so the first difference right on this here counts the number of classes that were born at or before ki and die sort of entering kj, right? So the second difference, so this is the second difference, right? The second difference counts the classes that were born at or before ki minus 1 and die entering kj. Okay. All right. So then it's easy to convince yourself that that difference then tells you the number of classes which are born specifically at the point ki, right, and die entering kj, right? So yeah. Okay. So this is all the classes which are born at or before ki and die entering kj. These are ones which were born at or before ki minus 1 and die at kj. So the difference is exactly the classes which are born at ki and die entering kj. Okay. So all right. So anyway, so the point is that this is the multiplicity, if you will, of the number of classes. It's like which were born. It's like at I and die at j, right? So so the P persistence diagram. Right. Which I denote by, so let's just call it DGM, diagram P of F, right? Involves sort of drawing points at each of these AI AJs, right, with multiplicity mu IJP. Okay. So these multiplicities only are defined for I less than j, right? So these are only defined for I less than j. So all the points sort of lie above the diagonal. And then for technical reasons, we're going to add, it's like the points in the diagonal with infinite multiplicity, and we'll see why that is in a little bit, right, for technical reasons. We also add points sort of AI along the diagonal. Sort of with infinite multiplicity. Okay. So you can ask, what are these beta ij's? All right. So how do you interpret that? Okay, in the context of the persistence diagram. Okay. So beta, so let's just say beta KLP is the number of points in the upper left quadrant with sort of a corner at AK AL, right? And then the quadrant is closed along the vertical, the vertical right-hand side. And open along the horizontal. Lower side. Okay, so if you have a persistence diagram, you have a point AKAL, right? Then you look at this quadrant, right? And you count the number of points together the multiplicity, and that is going to give me beta KL persistence. Okay, anyway, so that leads you to this fundamental lemma of persistent homology, which more or less says that if you have the persistence diagram, it's like then you can go back and forth, it's like with the betas, right? So this is the fundamental lemma. Of persistent homology. Says that if you have this filtration, then for every pair of indices, where k is less than or equal to L, it's like, and they're both between n 0 and n inclusive, right? And every dimension P, right? Then the Pth persistent Verdi number, well, that's actually really a statement of this, right? Beta KLP, right, is equal to the sum for I less than or equal to K, sum from J greater than L of mu IJP, right? So this of course is really just a statement of what I had said here, right? That you look at this quadrant, the upper left quadrant, right? With it's like this closed side and this open bottom, right? And you count all these it's like mu's, it's like which tell you the multiplicity, it's like of classes which were born, it's like at the ith point, or the ith complex, and then dies entering the jth complex. Oh, I'm sorry. Yeah. Okay. So that's exactly what this is. So again, it's like this is an important property because it basically says that the diagram, the persistence diagram, where you plot, it's like the birth and deaths positions. It's like of all the homology classes, if you will, right? Then encodes all the persistent homology groups, right? So So the point is that the persistence diagram encodes all information about the persistent homology groups. Okay, all right, so let me just stop here for now. Thank you.